All right, welcome everybody to this week's seminar series on string pheno. We're very happy to have Veronica Collazuol as our first speaker from the IPHT in Saclay, and she will tell us about E9 symmetry in the heterotic string on S1 and the weak gravity conjecture. Please go ahead.
Okay, so thank you very much, and thank you for inviting me here to speak about the presence of the E9 symmetry in the heterotic theory on S1 and the weak gravity conjecture, which is the topic of this paper with Alvaro and Mariana. So the moduli space of the heterotic theory on S1 has been completely mapped in this paper by Feynman, Grania, Nunez in 2018 in terms of symmetry enhancement at finite regions in moduli space. So a natural thing to do was to extend this scan to infinite distances in moduli space, which is nice also in connection with the predictions from the low energy point of view. Indeed, the symmetry enhancement framework pinpoints specific regions in moduli space where there are massive vectors becoming massless. On the other hand, at the infinite distance in moduli space, from, for instance, the Swampland distance conjecture, it is predicted the presence of an infinite tower of states that become massless. Moreover, if to this infinite distance limit is associated also gauge coupling that vanishes, then the lattice with gravity conjecture predicts a full lattice of states that become massless. And so it would be nice to understand how these three observations fit together, in the sense that if the Swampland constraints would predict the presence of infinitely many massless vectors becoming becoming massless, then from the symmetry enhancement point of view, we would expect the presence of a gauge group which has infinitely many generators. So just to set the notation, we consider the heterotic string theory compactified on a circle given by this coordinate identification in units of alpha prime, with metric given by the radius square. So this theory has a 17-dimensional moduli space parameterized by the radius of the circle and the 16-dimensional Wilson line. And the 9-dimensional heterotic states are labeled by the charges, which are the winding and the momentum along the circle direction, and the momentum along the heterotic torus, which in our case belongs to the root lattice of E8 times E8, even though, as we will see, the generalization to the SO32 theory is straightforward. So it states as the following internal momenta. These are the left and right momenta along the circle direction, where the plus here refers to the left momenta and the minus to the right one. And these are the momenta along the heterotic directions. And if we arrange them in a vector, this is found to belong to a Lorentzian lattice with signature 117, where 1 indeed is related to the right sector, which is called Noreen lattice of the compactification and is found to be even and self-dual. The theory has the following spectrum given by the mass condition and the level matching condition, which depends both on the left and right internal momenta and on the left and right oscillator number along the worldsheet. This is invariant under T duality, which in this case is given by the group O117Z. So since the momenta depend on the charges of the state at hand and also on the background, the spectrum depends on the point of modular space we are considering, and in particular, the massless spectrum, which is of interest for us, does. Indeed, if we want to find the massless vectors, this can be a signature of the gauge algebra which is present at that particular point in modular space. And specifically, if we sit at the generic point, the only solution to these constraints is given by states having vanishing charges, vanishing momentum 1 and heterotic momentum, and so vanishing internal momenta. And there are 18 such states, which are respectively the right and left Kaluza-Klein vector along the circle, and the 16 E8 times E8 Cartan's state. And the group that these states give is U1 right times U1 to the 17 in the left sector. Then at special point in moduli space, namely the fixed point of the T-duality group, there are additional solutions to this constraint, which have non-trivial left momenta. And so there are additional massless states that enhance the group from the left part of the group from U1 to the 17 left to a generic group G of rank R, which is less or equal than 17, times some product of U1s in such a way that the total rank of the left group is 17. These additional massless states are called root vectors, and the group G can be recognized thanks to them, since their internal momenta, once expressed in a suitable basis, turn out to be the roots of the group G, which have been classified completely in this paper, as I already told you. So just to give an example, in case we don't turn on any Wilson line, then the enhancement pattern is the same as we can find for the bosonic theory compactified on a circle, namely for a generic radius, the left group is E8 times C8 times U1, which is enhanced to SU2 in the case of radius equal to 1, so the self-dual radius. But then the presence of Wilson line makes the enhancement pattern much richer. And for instance, just to give an example, for this value of the background, we have the gate group, which is SO34. So another equivalent way to read the algebra, instead of considering the internal momenta of the root states, is to use the operator state correspondence and compute the commutators of the zero modes of the holomorphic currents associated to each massless state. So here, just to be concrete, I will focus on the case of the group E8 times C8 times 1 for vanishing Wilson lines and generic radius different from 1. So here the massless states are the E8 times C8 Cartans, the left Kaluza-Klein vector, and the 480 E8 times C8 roots. To each one of these massless states, we can associate a vertex operator, and from this read the holomorphic conserved currents associated to each state. So here the index I will refer to the E8 times C8 Cartan, the 9 to the circle direction, and the alpha to the roots of E8 times C8. And so if we expand them in their own modes, we can define the zero mode of each current as J alpha, given by the contour integral of the full current. And here my notation is that the zero mode differs from the full current by the absence of the dependence on Z. And if we compute the commutators of these zero modes by using the OPs of the full current, we see that indeed the structure constants we find are the E8 times C8 times 1 ones, and which I show here. So a very useful tool to find all to study the symmetry enhancement systematically without having to go through the massless spectrum in each case is the extended linking diagram of the Narain lattice, which is described, for instance, in these two papers. So here I show it in a way that makes manifest the embedding of the root lattice of the 8 times C8. And so in particular, I label each vector in the Wilbein basis with the winding momentum, and then the E8 times C8 momenta, like with these, with the momentum under the first E8 and the second one under the second copy of E8. So to build the full extending linking diagram, we start with two copies of the E8 linking diagrams, which with its node charged under the first and second copy of E8 with the simple roots. Then we extend them through the highest root, alpha 0 and alpha 0 prime, which is also charged with momentum, which works basically as imaginary root. And so we see that both the E8 copies are extended in the same way, namely with the same imaginary root, which will be useful later. And finally, we join together these two extended E8s through a central node, which is given momentum and winding and no heterotic momentum. So each of these 19 nodes basically is related to a value reflection that generate the T-duality group of the theory. And moreover, each one of the nodes is also associated with a codimension 1 surface in moduli space, which is given by the condition PR square equal to 0 for each one of these charges vectors. And since these planes, these codimension 1 planes are fixed under T-duality, then they are actually boundaries of the fundamental region of moduli space. So this diagram contains information on all the possible enhancements we can have in the 9-dimensional theory and on the point of moduli space where they appear. In particular, if we want to find if and when a certain group G of rank R can be realized in the heterotic setting, first of all, we have to make sure that it can be embedded in the extended linking diagram by deleting at least 2 nodes of the full diagram in order to get the linking diagram of the group G. And then to understand at which point this is realized, we have to verify these equalities only for the nodes we kept. So just to give an example, if we want to understand where SO34 appears, we can see that it can be embedded in the full extended linking diagram by deleting the nodes 8 and 1 primes. And so this is indeed realized in the heterotic theory. And then to understand the background that gives such an enhancement, we have to satisfy all the equations apart from the one for the node I equal 8 and I prime equal 1 prime. And so the solution of this set of equations gives this background, which is the same I showed you before. So from this, we see that indeed the 9 times E9 root lattice can be embedded in the full linking diagram, extending linking diagram. And so to see the background for which it is realized, we can saturate all these equalities apart from the one of the node C. So since these equations are given in terms of a rescaled Wilson line in terms of the radius, we see that for R going to infinity, these are all satisfied apart obviously from the one with the node C for any finite value of the Wilson line. And in particular, from the algebra point of view, we will see that all these cases are equivalent to the case without Wilson line, which I will focus on for the moment. Actually, even though we only deleted 1 node from the diagram, which seems to be against the prescription because it seems to enhance the rank of the group, actually this is not the case because remember that we extended both the copies of E8 with the same imaginary root. And so if we take into account this identification, the rank of the group that is actually realized is 17. The states that become massless as R goes to infinity are the momentum towers of the E8 times C8 times C1 states. Here are the Cartans and here are the roots. And indeed, if we look at the internal momenta of the roots in the winding and momentum bases, we see that they are indeed the roots of E9 times C9, namely here we have the extension of the first E8, here of the second, both with the same imaginary root. So we then checked if the extending linking diagram gave us somehow a meaningful answer even at the boundary of moduli space by trying to compute explicitly the commutator of the 0 modes of the currents. So from the vertex operator of its massless states, we found this asymptotically conserved current, which is made from the finite algebra current, which I show here for the Cartans and for the roots, times an exponential factor that accounts for the fact that all these states have momentum. Here I show also the OPs among the compact fields in the case of 0 Wilson line, which will be useful to be compared with the ones that are needed for the finite Wilson line case. So if we define again the zero modes of the full affine currents through the contour integral in the complex plane, we see that they indeed satisfy the E9 times C9 commutation relation with the loop part of the algebra and with the central extension part, where the central extension is given by the circle direction, as is indeed shared between the two copies of E8. So if we wanted to turn on some non-vanishing Wilson line, the computation would go through in the very same way, except for the fact that we should redefine the heterotic coordinates by a translation along the circle proportional to the Wilson line. And so the only modification we should do is to change the x to x primes in the finite algebra currents. The computation would be the same because if we computed the OPEs of these among the redefined compact field, we would see that they asymptotically would be actually the same as the original ones, namely the x primes are orthonormal as r goes to infinity and are also orthogonal to the circle direction, so that the algebra that the zero modes obey is the same. Moreover, we could also have focused in the dual case with r going to 0 at 0 Wilson line, and we would have found the same answer where the massless towers now are the winding instead of the momentum ones. Finally, since in the computation we didn't actually never have to specify what the roots were, we could also have carried on the same computation also in the SO32 case, and where we would get the SO affine 32. So we see that the SO32 affine and the 9 times C9 are the only two algebras that can be realized at infinite distance, and they correspond to the compactification limits. So here I show in particular a 3D slice of the E8 times C8 heterotic moduli space in 9 dimensions, where the vertical direction is given by the radius and the planar ones are two components of the Wilson line. So as we go to infinite radius and finite Wilson line, we get indeed E9 times C9, where, okay, from now on I will always forget about the identification. And in these limits, the theory decompactifies to the 10-dimensional E8 times C8 heterotic one. On the other hand, if we started with SO32 theory, as I just said, for infinite radius and finite Wilson line, we would get a fine SO32 decompactifying the theory to the 10-dimensional SO32 one. But since these two theories are in 9-dimensions are actually the same, we would expect to get the SO32 decompactification even in the first case and vice versa. We find that this is actually the case because if we look at r going to infinity in the E8 times C8 perspective with this Wilson line, so we see that r going equals 0 point, which is at the boundary of the fundamental region, we would get a fine SO32, and so the compactification from the E8 times C8 frame in 9 dimensions to the 10-dimensional SO32 theory. In the same way, for r going to 0 and this Wilson line with 8 1/2 and 8 zeros, in the SO32 frame, we would decompactify to the 10-dimensional E8 times C8 theory. Obviously, in this case, the towers are not the plain momentum towers and as in the other description, because all the massless states have all momentum winding and also heterotic momentum, which are labeled by some integer. But anyway, we see that the towers that are predicted by the Swampland distance conjecture are exactly the one that turn the algebra into an affine one. Another interesting link we can make with the Swampland conjectures is the one with the weak gravity and repulsive force conjectures in their lattice versions that are presented in these two papers here. So, as regards the lattice with gravity conjecture, for each point in the charge lattice of a multiple E1 gauge theory consistently coupled to quantum gravity, one should have a super extremal state, namely a state for which the charge to mass ratio should lie outside or at the boundary of the black hole region, namely it should have a charge to mass ratio which is bigger than the one of an extremal black hole. as regards the lattice repulsive force conjecture, under the same hypothesis, at each point in the charge lattice, we should have a self-repulsive particle, namely a particle for which two identical copies, which I label by 1, once put far apart, are repulsive, or at least a vanishing force among themselves. So these are not the two currently accepted versions of these conjectures, because, for instance, orbifold compactification only satisfy a sublattice version of them, but we never actually had to refer to these refined sublattice versions, because the heterotic theory compactified on a torus as a full lattice in the charge space that that satisfies these constraints. And moreover, even though they are actually two different conjectures and are not equivalent in the presence of massless particles, actually here they agree in our case, and they both give this bound for the mass once we restrict to the Cartan sector of the gauge group. In
Veronica?
the case of a black, yes?
You have 5 minutes.
Thank you. In the case of the black hole computation of the extremality bound, this was computed by Sen in 1995. So the towers that become the E9 times C9 vectors saturate actually this bound, because they are VPS states. And in particular, if we want to extend this bound to hold also at the boundary of the moduli space, we should restrict to the sector where the computation is the gauge groups are perturbative. And so if we want to extend to R going to infinity, we should look at the sector with zero winding, where indeed the computation can be trusted. Anyway, this doesn't, the full towers have zero winding, and so we're not throwing away any state that we are interested in. So if we turn off the winding and we re-express the extremality bound in terms of the gauge coupling with respect to the Cartans of the E8 times C8 times and the graviphoton, we see that we find this formula, and in particular, since the gauge coupling vanish as the radius goes to infinity, the fact that these states are BPS at any point basically of moduli space tells us that the gravity and the repulsive force conjectures predict an infinite number of massless vectors as R goes to infinity. And so this is another proof of the tight link that we have between the presence of affine algebras and the quantum nature of the system, because the vectors that become massless due to this bound are exactly the one that then arrange into affine representations. So just to conclude, in our work, we show the presence of affine enhancements at the boundary of the heterotic moduli space. And okay, the presence of affine groups was already discovered in 1999 in F-theory dual in this paper. And moreover, we showed also that only the 10-dimensional algebras have an affine counterpart, which was stressed in this paper by Lillertz and Weigand in 21. Always in the F-theory dual to the 8-dimensional heterotic theory on a torus. Moreover, we also show that we could have argued for the presence of infinitely many massless vectors, also from the effective point of view, effective field theory point of view, by linking this with many Swampland conjectures. And finally, for future works, obviously it would be nice to extend the study of the decompactification limit also to the lower dimensional heterotic theory, which, okay, the next step would be the 8-dimensional one. And here we already have somehow the dual answer in the F-theory perspective. Thank you.
All right, thank you very much, Veronica. Are there questions? Okay, so while people think about questions, can I ask just a quick one. Can you remind me? So you had a discussion where you were only looking at the Levy type branching of the affine Dünkin diagrams. Are all of the gauge groups that you get in 90, are they all of Levy type, or do you have some irregular subgroups?
So I mean, I didn't really understand the question. What?
In the beginning, you were describing, here with the branching of by deleting nodes. Can you reach everything just by deleting nodes, or are there sometimes also subalgebras that are not obtained by just deleting nodes?
No. Here you get in 9 dimensions with the Dünkin diagram. You get the full answer, all the possible algebras you can obtain, and then obviously one has to look for let's say the global structure, but still it's everything is contained here.
Okay, so always by just deleting the nodes you can get to all these algebras. Okay, thank you. And for the extension to lower dimensional case, you just have to do it, or you expect there is any problem? Yeah,
let's say for the extension is not that easy, because already in the compactification of the heterotic theory to 8 dimensions, there is not just one Dünkin diagram, and we don't even know if there are finitely many. And so here somehow we could at least have some indication of the points in moduli space where to look. Because indeed we see that, then we checked also with the computing explicitly the algebra, but still from here we could see that we had to look at R going to infinity for finite Wilson line, and so this was helpful. So in 8 dimensions, actually this is not the case anymore, and so one has, to find some more general patterns for to understand which are the right decompactification limits to look at, and what are the algebras one can find there.
But would they all be covered by the Kulikov models of Timo?
Yes, I would say so.